Okay. Nikki's hand is playing at the time. So please come on in, sit down. Prepare your rotten eggs and tomatoes for throwing.
Is our JabberScribe here? Is somebody willing to JabberScribe for us? Looking for a hand?
Okay, cool. So where we're at, we actually got through all of that this morning, and I was glad that we had an extra hour for the design choices document because we used it, but we're not done with that discussion, so we've got a little bit more to do. And then we'll look at translation and then the way we use addresses. So, Victor, where are you? There you are. Okay. Yeah.
Scroll all the way down. Left off. So we left off here, but I'm going to go to the next slide. This slide we left off, and there was comments before we broke, was around the use of the word private. Started to have a little bit of discussion about, yes, they're functionally different. They may be used sometimes in similar positions, but after we had a little bit of time to discuss it this afternoon, myself and Philip, based on the feedback we already have on all the NAT and ULA discussions, et cetera, the proposal is we're going to do a full rewrite of section 2.1 to include a lot of those comments and incorporate the comments we had today. And we're going to remove all of the discussion about V4. It's probably best, which will automatically get rid of the association to private. We're going to pull that pieces out because that seems to cause a lot of consternation. The other point that we wanted to mention was the authors proposed not to expand. I know there was a comment about expanding the survey information to talk about trends and stuff. So we think that's valuable information. The thing is, it kind of goes out of the scope of where this document was, where it's supposed to talk about, here are the options. If there's a discussion about those interim positions, we're going to add a little bit of text to say that some of these might have been interim states and networks, and they may have been used to get to another state in terms of what IETF protocols you use. We thought that going into a discussion about trends was going outside the scope of where the document was trying to discuss, which is, here are the different combinations of protocols you could use for V4 and V6. The other point I wanted to talk about, I'm trying to remember, Phil, it's just there. Oh yeah, earlier on when we talked about the NAT discussion, ULA addressing, one of the things I noticed, and it didn't click till after we discussed it this afternoon, was the document scope, and maybe this is why we have to rewrite the section, we were talking about addressing for the internal parts of the network, not the end hosts and subscribers. However, when most of the feedback appeared to talk about a lot of breakages in applications, would typically, a lot of the concerns were about the end hosts, and we were talking about the internal parts of the network, your router links, and a lot of those components. So as part of the rewrite of section 2.1, we're going to clarify that much further and show what parts of the discussions we're talking about when the interior parts of the network versus the edge parts of the network, if that makes sense. Because readdressing is very different when you try to readdress your entire internal parts of your network, recreating all your BGP config, all your LDP config, redoing all your configs from scratch, versus just end host reslacking an address or doing other DHCP option. There's very different things at play there. So as part of the rewrite, we're going to clarify that much further to make it a little bit more clear. That makes sense? And then we have feedback from Jan and Tim. So when we're going to flip, that was on version 9. We're going to take their feedback, put it into a version 10 with the full rewrite. And then what we're going to ask at that point is, we had some good critics out to this morning. What we'll do is we'll ask them to review our information first to see if we get a position on consensus before we go even further, because they'll provide us probably the best initial feedback on the rewrites, make sure we have their concerns taken care of, and then we can kind of get a more expanded set of inputs from the rest of the folks before we try to push for a last call. So that's kind of where we landed. So if we pull out the private discussion and the V4 stuff, we feel that's probably going to be a better way of moving on this. So any comments at this point? Seems like a very anticlimactic end to a heated beginning. Good? Okay. That's it then. Anything you do?
Cool. Thank you. Great.
Okay, good afternoon. This is Professor Xing Li from CERNET. And this is actually individual submission, but it's the RFC 6145 bits. Okay, this is like 3 things I like to cover. The first is a little bit review of the RFC 6145. And the second, why we put bits, what changed, and the next step. Okay, so RFC 6145, that's for IP ICMP translation algorithms. It is the building blocks of RFC 6146. It actually has the stateful NAT64, and RFC 6219, that's IVI, stateless NAT64, and RFC 6877, it is 464 X-late, stateful double translation, and RFC 7599, that's MAP-T, stateless double translation. And currently this RFC 6145 referenced by 31 RFCs already, and there are 26 active drafts reference to this one. So it seems we need to update.
So you're saying it's been completely unsuccessful, right?
Yeah. Yeah. Okay, so why it speeds? Mainly there are 3 things. The erratum, atomic fragments, and the address mapping algorithms. A little bit explanation for that. Okay, actually this is quite straightforward. The original one is, it is, okay, 6145 is obsoletes RFC 2765. And in the editing work, there is ambiguities because for extension headers, RFC 6145 does not really precisely describe has to skip those kind of lengths of the extension header. So we put these things back. So that's the first thing addressed in this RFC 6145 bits. And the second, actually, this is the reflection of the work in 6-man. The current 6-man working group RFC, that's duplication, the generation of IPv6 atomic fragments. And actually, fortunately, the original RFC 6145 addressed this issue already. There is a workaround. And then these bits just make that as the default and the only choice. And so those are the details for that, because actually in previous IETF meeting, we explained that, and that's actually originally from IETF 67, the same presentation. So I skipped that. If people want to discuss, we will come back. And the third thing is, in the time of RFC 6145, there are only one address mapping algorithm. That's RFC 6052. However, after that, there are some other address mapping algorithms proposed. So, and in the previous IETF, we are discussing if we should put precisely EAM, explicit address mapping algorithm, integrated into these bits. However, the decision in previous RFC is make it a separate document. So it's make life much simpler in these bits. So it's just mention the related address mapping algorithms. And the should is RFC 604052 is the default. And then the current draft in IEST, actually, that's the EAM. So that's also the should. Another is RFC 6791. It's just for stateless source address mapping for ICMP v6 packets. And also mention RFC 6146 net 64 and RFC 6799 map-T can be supported in a stateless translator. This is for stateless translator. For sure, if it's stateful translator, then those kind of RFC should be must, not is the must, not the may, but because this only address the stateless translator, so that put may. So that's basically the things. And based on what we believe the next step, if there is no objections, there will be 30 days IETF last call and take this as the AD sponsored draft. So this is the things. Any questions or comments?
Okay, comments?
Pierre Pfister, I just would like to ask a question. One of the changes you propose is to enforce that if there is an extension header after the fragmentation header in IPv6, I don't think it's in your slides today. You ask that the translator should drop and log the packet. Why? What's the problem of having an extension header after the fragmentation header?
Because IPv4 cannot support any extension headers, right? So if it's not really
And couldn't we
drop,
remove it?
It's not really drop. It's just ignore those kind of extension headers and
Okay. So that's not what I understood by the text. The text says drop, so drop is like you don't translate.
Well, so the security header would always follow the fragment header. Right?
Okay, yeah.
Okay. And just another question is, when you say those should and may in the end of the presentation, does that mean that if I want to implement translation, I have to, well, I should implement those mapping and I may implement the other mappings?
Oh, you mean for this one, right?
Yeah, for instance.
Okay, for stateless translator, the RFC 6052 is the default. Okay, so you mentioned precisely EM.
Yeah, the thing is, I'm a bit surprised to see a should here. Like, If I just want map T, I will implement map T, and I don't see why I should implement the others.
Yeah. Okay, as I just mentioned, this is for the stateless translator. If it's a map-T translator, then the map-T should. So it's a little bit confused for the wording or whatever. Okay, like map-T, state4, net64, all use these arguments.
I understand there is a list of examples, but the should means that if I don't do that, I should expect problems. But I don't think there would be problem if I decide to not implement one of the mapping, if I want just map T in the end.
Mm-hmm. Because the wording is good. Okay, thanks for these comments or thing.
Okay, so it sounds like there's an update in order regarding the successive extension headers, because there is at least one possibility after the pregnant header. So.
Okay. Any other comments?
Okay. So my suggestion then is that you update it with respect to that. And then we'll run a working group last call, maybe the first half of December.
IETF last call.
Well, working group last call, and we'll get any other comments that are on the table.
Okay.
And then I would imagine that Joel will take it to the IETF last call in January.
Okay.
So during Chinese New Year. Well, correct, but we've been discussing it.
We can have a conversation.
And
Process question. It's not a working group document. Do we last call it?
do we want to adopt it? Does our area director want us to adopt it? Sorry? Well, he made his.
I don't see a problem with you doing that. I also like, if it looks like we have reasonable consensus on it, it is an update, so we could just process it. Like, but I mean, the thing is if we're going to take it forward, like if I were to sponsor it, for example, like I would still want to know like that it had decent review. And so.
Well, and that's my point with the working group last call.
Yeah. So if you would prefer to not process it as a working group document, but take it forward in some other fashion, and you asked me, I would probably say yes, because I don't see a problem with that.
Okay.
So that is an option that is available to you.
Well, so now let me ask the working group. Do you guys want to adopt this as a working group draft? If so, please hum. If not, please hum. No humming whatsoever.
Philip Matthews, why is this draft being done here?
It's being done here basically because there's no obvious place to do it, and it wound up here.
Okay.
That was a discussion between one of the authors and the area director.
Yeah, I mean, we should do maintenance wherever it's most appropriate. And like what we're looking for ultimately, like, is if we if we have a place where we can test out our theories about the document, that's great. I have a whole working group set aside for if there's no working group to do a document in that exists.
So the only problem I see is, isn't this going to be a standards track document? And are we actually allowed to do standards track documents in this working group?
Yes, you can. And in particular, you know, we're doing maintenance on something that has already been through that cycle. So I think we're actually probably okay there.
So dear AD, I do not find working group consensus to adopt this document.
Yep. So we'll deal with it elsewhere. Thank you.
Thank you.
Okay. With that,
Fine. I mean, what we're here for is review. So we have that now.
Stand in the pink box.
Okay. Then please feel free to sit there.
Remote participants, in order to see you, you have to be roughly in the box. Maybe you can.
All right, good evening. I'm Dave Plonka. I'm with Akamai. And there's this happy coincidence for this IETF that the IMC happened just before it. So last week we had a 3-day ACM Internet Measurement Conference, and I presented this work that I did with my colleague Arthur Berger there. For about 2 years, we've been analyzing as deeply as possible what's going on in the IPv6 address space by looking at the IPv6 addresses that hit the Akamai platform. I was somewhat concerned that in the 3-day conference with 180 people there and or about 70 students, that this was the only IPv6 work presented there. I hope I did a good job of reminding all the students along the way that they could expand their studies and that they will need to change things to work in the IPv6 space, but I'm trying to be somewhat of a bridge between those two communities, the research community there and the operational community and the standards community here. So if you have thoughts after the talk about those kind of things, I'd be happy to hear them. And also, I sort of feel like, at least for myself, we're not doing a very good job of adopting a researcher because they seem not to know what's going on in the V6 space. So I'll show you what I showed them and see if you think it's valuable. So the premise of this work is that IPv6 is not merely a bigger IPv4. And that to understand the structure of the IPv6 internet, we need to understand how addresses are used and assigned. And the urgent operational issues right now, what I see with the current level of native V6 activity is that we need to do things like be able to select intelligently targets for active measurements. Of course, with transient privacy addresses, it's very hard to pick stable targets. If you want to census or survey it just to see where we are, and I'll show you the way we're doing that based on addresses and the visualization, we need to understand the structure. And then we want to inform things like logging and data retention because we're seeing something like on the order of 10 billion IPv6 World Wide Web client addresses in a month. So think of that's about 1 billion in the V4 space and about 10 billion in the V6 space. So the same data structures and the same retention policies might not work. And then lastly, and the thing that actually spurred us to, or reminded us to present here is Eric Nygren, who's on the V6 ops list, said there's a lot of host reputation conversation going on in the V6 community, which is good because there's a lot of activity there. And the work we've been doing happens to be targeted right at this. And I'm calling it Prefix Intelligence. How do you, at any length of IPv6 prefix, how do you know how it's used? And how might we apply that to things like access control lists or rate limiting filters in the web and things like that. So I'll show you how far we've gotten or haven't with that process and see if it's useful to you. So the way we tackled this problem is to do 3 things. We engaged in a continual measurement study of all the World Wide Web client addresses that touch the Akamai platform over the last 2 years. And it's an ongoing study. We're operationalizing this, so this is part of our normal business in Akamai right now. And from the measurement study, then we have all the visibility into all these active addresses, and we developed 2 classification mechanisms for the addresses. That one is targeted at the temporal aspect of the address, how long-lived or short-lived it is, and the other aspect is the structural component. Where are they relative to each other in a vast, relatively empty address space? So those are the 3 things we'll touch on, and then I'll bring you right up to date with the most current visualization of the entirety of the V6 address space that we have right now. So you guys know this, I think. The challenges in studying or monitoring it, it's a huge sparse address space. A lot of people still don't know that V6 addresses are just completely different in kind. They're so big, you can do many different things than you can with V4. And already we're seeing billions of them on on the scale, like in terms of a week, we'll see 3 billion active World Wide Web client addresses. One of the ways that people, or there's a number of ways people have been measuring the progress with the V6 internet running simultaneously with V4. And one report, for instance, earlier this year, Vince Cerf said 3 to 4% of internet users have V6. And if I ran the numbers with estimates of how many in the world had it, that's in the 100 million range. And I don't disagree with this. That early this year, I think it was a little low. And I'm doing it, counting this in a different way than other people are. We're not using ratios of hits or volume of traffic. We're using actually counting the active addresses that we see and trying to intelligently decide if we're counting 64s or full addresses or whatever. But there are other reports out there. For instance, Matthew Prince with Cloudflare tweeted earlier this year, right about the same time, that nearly 1/3 of IPs connecting to Cloudflare's network are now V6. And when I said this to the measurement community at IMC, I just said, what's wrong with that statement? Well, what's wrong is it's completely ambiguous because you don't know over what time frame, right? Is it a day? In a day, I might see 10% of the addresses being V6. In a week, though, I would see 3 times the addresses being V6. And in a month, I would see 10 times the addresses being V6. So based on our measurements, I can reverse engineer that he meant in a day here, because anybody that runs a big service right now that's still stacked, you're going to see about 1/3 of the addresses in a day be V6 if they're from typical World Wide Web clients. So we're going to try to, I guess, at least for the research community, what I was trying to do is, by the end of the talk, I wanted them to understand and be able to intelligently comment on observations like this. I gave them a very short introduction to different kinds of IPv6 addresses. I will skip that here, but will tell you that the basis for this research is we take the addresses and bloat them up the way they look completely, and then realize that interesting things visually, like if I'm just eyeballing these addresses, individual patterns of characters like the UI64, FFFE, or individual characters and runs of zeros, those are important because human beings like to structure things so that they can understand them. And at first you can eyeball these and we can classify some of these just that way. The first one is an UI64 address. It very likely has a MAC address embedded in those blue characters there. The last one looks for all I can tell like a privacy address, some big random number in the low bits. And then the other two look like there's some kind of hand subnetting, or like the way we might see if somebody's familiar with V4. So that's about as far as we can go just by eyeballing these. And so introducing is the notion of classifying the address. Like you could say, first, the class of addresses that we're going to look at are all the addresses that are active World Wide Web clients. That's a subclass of all the active IPv6 addresses in the world. But this notion of class, I don't mean like class ABC or a CIDR block class. I mean any kind of way you can create an equivalence class of addresses. They could be all the addresses that are in the same physical location. They could be all the ones that have exhibited malicious activity. These are all ways of classifying addresses. And I'm going to, I guess, posit that what you want to do is classify the addresses and then use those as an ingredient for host reputation and how you would treat them. So I mentioned the measurement study. Here's the data set that we use for it and sort of what we see at Akamai right now. The first data set is active IPv6 World Wide Web client addresses, and it's completely passive. These are all the World Wide Web client addresses that, as of say May of this year, hit 55,000 of our servers that were IPv6 capable and we were hosting IPv6 content on. As of September, the most recent numbers I have, these represented clients in 8,800 BGP prefixes and 4,923 ASNs, which is 47% of those that are advertised in the BGP right now. So that's surprising to the research community. Maybe it's surprising to some of you. Only about half the ASNs that advertise BGP prefixes do we see client activity from. Those numbers are quite a bit up from March of 2014, which was the start of this study. And then in the paper, which is linked in your agenda for this session, we also did a study in the router space. And the way I think, so these are V6 active addresses that were discovered by Traceroute. And that set of addresses, of course, has different characteristics that are interesting, but we don't have time to talk about them here. It's covered in the paper. What I will tell you is, in the paper we used 3 million IPv6 router addresses that we discovered. We're up to 14 million IPv6 router addresses that we've discovered as of September this year. So there's a ton of them out there. And then to completely fill up the rest of the V6 address space, there's the server space, like where everything is hosted. And we did a separate study in that space. But today we're going to focus on these World Wide Web client addresses. So let's still background on the measurements. Here's what we see. So the measurement study was collect all the IPv6 active client addresses at 6-month intervals. So March and September of both 2014 and 2015. So where those dots are where we have the measurements, and we have all the addresses for a month. And what I do is I count them for a particular day. I happen to choose the 17th of the month as the day, and then we also count them over a week's time, starting with that day. So if we look, for instance, from say September of last year, we were at 199 million active IPv6 World Wide Web client addresses per day that the Akamai platform would see. As of September 2015, this year, we're at 470 million a day. So it's about the doubling that in deployment of V6 that most people have been saying over the last couple of years. If you look at traffic volumes, it's about a doubling. If you look at hits, it's about a doubling. If you look at Google statistics about the ratio of ones that prefer to use V6 over V4, there's about this doubling. So it's coinciding with that. The dark blue line up at the top, that's the raw number of addresses though. And you know there's a lot of transient addresses in there that you'll just never see again. So we can go down the 64 prefixes, which is shown in this light blue or cyan color, the next one down, and we're seeing 164 million unique /64s per day at the Akamai platform. And in some cases, that's actually, I mean, of course, if it's straight up Slack and there's nothing weird going on in network ID, that's one estimator of the number of active users in the V6 space for those prefixes. I'm sorry, is there a clarifying question?
Yeah, Jared Mach from NTT. So at the end of September, Apple released their new iOS and software updates that reweighted their Happy Eyeballs implementation. And I'm curious if you have data that shows a little bit past there as well, because we saw a doubling of IPv6 traffic on our network overnight.
That's really interesting. So that'll be exciting when either later this week or when I get back, I'll look at the data since then. But right now, this ends basically 1 week after, or 7 days after September 17th. I'll show you in this presentation. So there's a lot of activity there, and I was really excited to try to figure out how could we look at the entirety of the V6 address space, at least where the clients are. Well, in the past, this is a heat map for the V4 address space. You've probably seen this before, but basically you're mapping every possible location in the V6 address, or the V4 address space rather, somewhere into this rectangle. And sub-rectangles are other interesting things that are given out to regional registries and individual ASNs and things. And then here, this is lighting them up based on whether or not they respond. So dark areas here are the quiescent portions of it, and bright areas are where it's active. And that worked quite well, although you wouldn't use it necessarily operationally. It worked quite well to get kind of a picture of what was going on in the V4 space. Unfortunately, this technique doesn't work at all in V6 because you can't take a 125-bit address space and map it into pixels like this. It just doesn't work. And it would just be all black anyway because it's just dominated by darkness. So what we've come up with instead is this visualization. It's called a tree map. It's been around for decades. It's used sometimes in the stock markets and financials. It's used in various kinds of software engineering. But the idea here is you make those same kind of squares, but you proportion them by some metric you like. And what we're doing here is proportioning them by the log base to BGP prefix size. So this is one view into all the advertised BGP prefixes. And what we see is things like KDDI down here in brown. The colors themselves are just random, but they're sticky to the names of the networks. And then each rectangle is a prefix. Each colored rectangle is a prefix. And then, so their size proportionally, we see KDDI advertises a lot of space, Verizon down here, CenturyLink, there's Sprint Wireless that just came up in the last few months, and so on and so forth, down to just the thousands and thousands of that don't advertise very much space. And then the other dimension here, we have color. The color here we're using to measure the transience of the IP addresses, basically how ephemeral they are. And we'll see that a little more later, but just what I'm showing you is we have an effective two-dimensional presentation of what the entirety of the V6 address space looks like. Now let's go back to the measurements, and then I'll round this up showing you a web browser version of this where you can wander around and do data exploration in that visualization by drilling down and by changing the way they're sized to get an idea what's going on there. So this is that same plot over the course of the study, but this is the number of addresses or prefixes counted in a week's time. One of the things I forgot to mention was the key here. The first three transition mechanisms that I'm calling kind of legacy transition mechanisms that do not use native IPv6 transport, we separate those away. So when I say blue other traffic here, it means all the things that I have no evidence that are not native transport. So I believe that's native transport in blue. And then we peeled off the other things that you could just do by examining only the addresses. You don't need to do an exotic thing to pull out UI64s or the MAC addresses in them. But anyway, what we see in a week's time is 2.61 billion IPv6 addresses per week and or 417 million unique /64s. So one of the potential limitations of this is that, of course, not every address that is an active World Wide Web client necessarily comes to Akamai every day. So that's one of the reasons why we use the week time. And the other reason why we use the week's time as well is to look at the multiplicative factor involved with addresses that change. So we see an increasing number of active /64s and a dramatically increasing number of active addresses, of course. Along with this study, we're releasing 2 data sets that allow us to make visualizations like the one I showed. And these green bars for March 2014 and March 2015 are the 2 times where we're releasing the data, and it's up on the Akamai technical publications list right now. So this was more to feed the research community, but so that it could kickstart students that want to study this. They have 2 years of data from a very broad vantage point to work from. If we drill down into, so all that other stuff was down in the weeds there. If we look at it on a log scale, we can see the first 3 transition mechanisms. This last time frame between March of this year and September, that was the first time I did not see those transition mechanisms counts increase. So that's probably good news. There was some thinking that maybe 6to4 disappeared quite some time ago. We still see 64.2 million 6to4 addresses hit the platform in a day. In a week. Okay, so now let's go into the first of the 2 classification mechanisms, the temporal classification. So the idea here is, if you just looked at those addresses, remember I said it looked to me like a big random number there. Well, you can't eyeball a random number. In fact, you can't analyze a 64-bit number and determine that it's random. It's too short a string. It's considered maybe impossible to detect randomness in such a short string. So what we do is, the other way you'd approach this, you say, well, those privacy addresses are short-lived, so let's look to see if they ever come back to the platform. So we take sets of the addresses and say, let's take, for instance, here on March 23rd, we see something like 350 plus million IPv6 addresses hit the platform that day. And then we have a sliding window 7 days before and 7 days after, and we count of the ones we saw on March 23rd, how many were there on the 22nd, how many were there on the 21st, and you can see you can determine the lifetime of the address. So we came up with a definition of 3D stable, meaning 3 days stable, 3 days separated by 2. If we see them active in that pattern across this sliding window of 15 days that keeps going on, then we consider it a stable address and likely not to be privacy, or likely not to be completely transient. Modulo the fact that I said before, because it's web hosting content, people don't have to come to us every day. So some of the persistent addresses will look transient, but hopefully over time we'll learn that they're not. So what's the proportion then of transient to non-transient? Let's just focus on the most current time frame, the most recent. As of about today, we see that 92% of the addresses that are used by clients that hit Akamai are transient. They're not 3D stable, and so therefore about 8% are over a week. Over a day. And then here's it is over a week. So maybe you guys would think 90% of the addresses are probably these privacy addresses in ephemeral, so that makes some sense. But what about for the /64s? A naive guess about how this would work, and I will admit to you that was my naive guess 2 years ago, was that the /64s would be stable and that we're only changing the addresses. But when we look at the stability of the /64s, On March 23rd, we saw something like 140, 135 million active /64s on that day. But of those /64s, the day prior, only about half of them were there. And the day prior to that, only whatever, something like 40% of them were. So /64s are not particularly stable in the client address space. And here's what it looks like then when we break it out. 14% in a day of the /64s are not stable. And it doesn't mean that they're necessarily transient. It means I haven't found them to be stable. But the confident ones that there are 3D stable is the rest. So something like 85% of them that we see in a day are stable. But we look at over a week's time, and the difference between these two, see, you can see this is kind of pretty stable across that time. But when we go to the week's time, we're seeing more and more of these not known to be stable /64s. And that's something we'll investigate. So now what I'm going to switch to is a light introduction to the analysis technique we use. You guys are used to TCAMs and things like that. You know, before that, you'll remember we used binary Patricia trees, or what's called the base 2 radix tree, introduced about circa 1990 in BSD Unix as an efficient data structure to store prefixes to do longest prefix matching in. And so in software analysis, this is still the data structure that we use. So what we're going to do is we're going to take that historically useful data structure, and I'm going to show you how that can be used as a tool in a reverse fashion to understand the structure. So instead of putting a structure into the database and matching addresses against it, we're going to take the Patricia tree data structure and populate it with all the active addresses we see, and use the internal nodes of the data structure to expose the structure of the internet address space. That's something that Kenjiro Cho introduced in a paper circa 2002, and I've been able to use it a number of times over in various studies. So to give you a little glimpse of what that's like, it's not a very good visualization technique because it uses screen real estate, but let's take 5 randomly addresses taken from a Japanese telco that had 12,000 active V6 addresses in a week, and punch those into a Patricia tree. So what you get is you put those 5 addresses in, and you get only a 4 levels deep structure. This is why it's efficient. You only have to do 3 comparisons to get down to the leaf. And then these solid circled nodes at the bottom, these are the active addresses themselves, and the other are these internal nodes. So what the little introduction I just gave you is, you punch those addresses in, I'm going to tell you that those internal nodes tell you something about the structure of them. So what it shows you is there's something, the internal nodes have a prefix length, and you only create another level when you need to do so to differentiate those 2 addresses. It's called the discriminating prefix length, okay? So the discriminating prefix length for any particular address is the parent node plus 1 in a Patricia tree. And so now I've annotated each of those addresses with their discriminating prefix length. And here, one of the addresses could be discriminated only at the 43rd bit, and the other ones were 63 and 64. So earlier this week, when I had 2 days holiday and we were walking around Tokyo, and I'm seeing all these trees on the side of the road that are these semi-manicured sort of giant bonsai trees. This one actually on the left here looks a lot like the way a Patricia tree populated with a lot of V6 addresses would be. And the reason that is because we've got at least 2 major classes. We've got ones that are in dense regions, addresses that are very close together, like they're hand numbered, and you've got ones that are very far apart because they use these random numbers. Well, a tree of this sort branches in the middle if the addresses are very far apart, like at the 64th bit, and they branch up at the top if they're very close to each other. So we have a way to discriminate these address classes and understand something of the structure. So we take addresses, and just like I showed you, we build a Patricia tree. This is the same thing I showed you before, but built with just 8 addresses, and I stretch it out so that the edges are the right length for the 128-bit address. And I'm just showing you the addresses in there. Now we flip it vertically the way a tree really grows, and I'm going to introduce to you, this is the visualization we use to classify an IPv6 prefix. It's called an Mra plot. So the relationship between the tree and the addresses in the Mra plot is you have the tree over there, and if I cut down the tree and fell it, it will fall this way, and all the branching that happens in the middle of the tree, which is where privacy addresses are discriminated, will fall into the middle of the graph. Things that are dense and close to each other will fall over here. And the volumes, the relative volumes of these are telling you this is how many /128s are aggregated in a /112, very dense. This is how many /80s are aggregated in the /64. So I'm gonna skip through this, but other than mention to you that the way that's constructed is not magic at all. It's very simple. All you do is go across all the addresses you see, and at every prefix length, you count how many unique prefixes of that size are active. So this is a plot on a log scale for that particular Japanese telco in a week's time of the 12,000 active addresses. It's saying it didn't have, they were all in the same prefix up until about the 40th bit. And then you go, once you're up to like past the /64, there are 100. By the time you get all the way up to count all the addresses, there's 12,000 of these /128s. So we go through that, and instead of just plotting that directly like I've done there, you make that MRA plot I showed by finding the ratios of adjacent bits, adjacent characters, or colon separated segments. It's described in the paper, but I just wanted to give you a hint that it's not some magical weird thing that I came up with. So let's use this Japanese telco example with the sample addresses inset there to give you a tour of what you can see in one of these graphs. What you can see is, if you look at the addresses, you can see the first time they're discriminated in the prefix, which is just past what would be the BGP prefix, which I've anonymized there. You see a 1 and a 2. Well, that 1 and a 2 are 1 bit different, and that 1 bit shows prominently right here. And then this sort of profile of these steps downward after the /64, that's the signature of privacy addresses. Because if you put a whole bunch of random numbers there, they will be discriminated in lesser and less, it'll need less and less of the previous bits or the early bits in that number to discriminate them from each other. This profile, these steps up over here, this is very dense address space. And think of this one like an odometer. In your car, the low order bit changes all the time, or the low order character changes all the time. The next one changes a little less, the next one changes a little less. So if you're going through sequentially and numbering hosts, that's the way it's going to look in this plot. So now immediately, if I just show you this, once you internalize those rules, you'd say, well, Dave, there's a mix of privacy addresses and dense addresses here. There are more whole addresses aggregated in 112s than there are in the /64, so you can get an idea of the ratio of dense to privacy addresses. Now, if we look at a completely different network, what would be important is it has to discriminate the address policy, right? In a completely different network, a US university with a relatively similar number of addresses, sample addresses there, we see tons of what look like privacy addresses. And sure enough, in the graph, that's all that you see evidence there. So now let's look at the entirety of the V6 address space. It looks like this. So this is everything aggregated across in this case, we used the March 17th one, which I think was 1.8 billion addresses or something like that. All it's showing you is that things you guys already know, that the BGP prefixes are from the RIRs and things, those are used to discriminate. And then there's a whole bunch of IGP prefixes that are doing discrimination over here. And predominantly, since predominantly the 90% of them are probably ephemeral addresses, you see only evidence of the privacy addresses. If you looked at individual prefixes, you could see the evidence of the densely packed ones. So we look at the overall and find these different characteristics now that we've classified the prefixes, and now I can select interesting prefixes to you. So the next graph here, this is 6 to 4, just to give you an idea how different the V6 address this is than the V4. In 6 to 4, since we pack IPv4 addresses between the 16th and the 48th bit, that MRA plot just in that segment, that's the way it looks for V4. And that's kind of one of the reasons why they gave up on this technique after they invented it some 13 years ago, because yeah, it shows that it's really dense in that space. But we can go in and look at other individual networks. So here we're looking at, for instance, the single ASN that has the most active World Wide Web clients, as far as we can tell from address counts, 167 million /64 is active. And what do we see here? Well, we see evidence of these privacy addresses, this thing going down here. We see the maximum aggregation possible between 48 and 64 bits there. That means every possible value occurs in the addresses we've seen there. Well, what in the real world causes that to happen? A pool of addresses that you traverse with your clients. Like let's say you put up 1 million addresses and you have 500,000 active clients, and if they move through it, you'll light up every address over a week and you'd get something like this. Here, a simpler model, and this is probably the very straightforward one that might be the best introduction for someone who didn't know V6 addresses, this Japanese ISP, they have zeros between the 48 and 64th bit. They've got some discriminating prefixes in their IGP over there, and they're using privacy addresses. So straight up, this is 2.18 million /64s. I would say in this network, you've counted the number of active users just by counting the number of active /64s. And to validate that assertion, what we did is we looked at the UI64s in it and saw that something like 95% of the time the UI64 was always in the same /64. So static /64s to users, and then something with slack inside. Now, if you believe some of the things I said about what those characteristics of the graph mean, this is, I think, one of the most entertaining sample MRA plots. A European ISP with 15.5 million active /64s in a week. We see this randomness here, which is privacy addresses, but you also see that same profile again right here, then interrupted, and again here. So it looks like there's possibly 3 random numbers in this address, and that, or at least if they're not random, they're sparsely separated, because that's what causes that step going down. So we looked at the distributions of the values in those ranges and found, sure enough, they're uniform here. So we have good evidence that this is a random number. This one is not uniform. It's most often 0 and 1, but then it's distributed across the space. Like we think it's something that a piece of customer premise equipment might do. If you gave it a /56 and it was responsible for coming up with this before it gave out before it was a slack router. So of course, the consequence then, if I want to count the users in this space, well, I'm not going to count /64s because there's random numbers in there that are not used in part of the routing. And that Patricia tree and this show us that even though there's information there, it's not pertinent to discriminating hosts, therefore it is not used in routing. So the portion over here is, and so a good start would be to start at something like this /40, because that's not injected with seemingly random numbers. So in this network, we've seen a single UI64. We're kind of using these as a guidepost to validate our findings, because the interface ID stays the same with the UI64 if it's a legit MAC address. In this network, we've seen in a week's time a single UI64 be in over 100 /64s. So if you count the /64s and are using it as an estimate of the number of users there, you would be off by a factor of about 100 and overcounting. In this network, though, which is a European university, it seems like some university administrator was given just a /64 for his whole department, and he was fine with it, and did some subnetting up here and put 100 hosts over here. So this one we validated by, once you find the dense addresses in the V6 space, now you have a recipe to do active measurements. I can do all the pointer lookups. I can't look across the whole space, but if I find a dense region, I can. So we did the pointer lookups here, and every one of them had a reverse name. 90 some of them were called DHCP v6- something, and 4 or 5 were called server names, like mail exchangers. So one of the things the density analysis that comes out of this does is it gives you a list of which prefixes are dense and which prefixes are sparse, such that we could do things like ZMAP across it, or you could do active scanning there and discover the hosts in between that don't come to a platform that's only watching them passively. So that was sort of the pictorial version of the temporal and spatial classification. In the real world, you actually need to know the values. You can't just look at a picture. So what we have is a way to, we've come up with basically a naming scheme for the prefixes. And it's something like you say n at p dense. So I'd say a dense prefix has 2 addresses active at /112. That's my definition of density that I'm interested in. And I would choose that based on how much of the address space I was interested maybe in scanning. If I wanted a smaller set, I would say, well, I need to see at least 10 active addresses in that /112, Dave, to consider it dense, and maybe we'll walk across it by doing PTR lookups, or I'll scan across it with something like ZMAP. So to sum up, then we introduced 2 different classification methods, one to isolate or to discriminate transient IPv6 addresses from the stable ones. And that lets you do lots of things like pin up ACLs or do rate limits based with the right mask. And it also it allows you to do active probing now. So that was one thing that not a lot of researchers have been doing active probing here because they didn't know where to look. So we find the areas where the action is in the IPv6 address space. The stable addresses were also good for targets for probing, because you can get the user's machine at home past the customer piece of premise equipment to respond, and therefore discover the entire diameter of the IPv6 internet, which sometimes is 1 or 2 bigger than the v4 internet, just because you can have globally routed addresses on the last step. So now let's switch into the current work, and I'll finish up with showing you this kind of fun way of looking at the space using these classifications. So actually, I'll show you this to you right in the web browser, the way that I do it. Okay, so that's that visualization in a web browser. In the lower left, it says BGP prefix size log2 scale. So as of September 17th, this is the way it looked. And now I can say things like, show me the active IPv6 space with these regions sized by the number of active addresses. So it morphs into this picture where now you see who's hitting the Akamai platform. Verizon /128 addresses here, Comcast there, T-Mobile up there, Sprint there, Deutsche Telekom, AT&T, Time Warner. These are the big guys that we see. And all the other ones are there, it's just they're small. If you want to see those, or they're smaller, I should say, you can zoom in on them. And each one of these rectangles is a prefix. And if you drill into that specific ASN, it will show you which prefix it is. And again, I said they're shaded by the number of transient, or the ratio of transient versus stable addresses we see there. So it's exposing something about the addressing policy there. Basically means you have something that you could scan in the dark areas, and in the light areas, there's a lot of transient addresses that are probably privacy. So let's pop back out to the top level and look at it at a different dimension. Well, active addresses, we know that's going to be exaggerated by privacy. So what about active /64s? Then it morphs into this. It says Verizon proportionately is even bigger. T-Mobile's really big. Sprint is. Deutsche Telekom is big. A lot of the same people, but different relative sizes. Then we can look at something like, well, where are the transient /64s? Now, this is one of the most fascinating outcomes of the research to me. These networks change the /64s a lot. They don't come back. So if you're counting /64s, it exaggerates the number of users, but it's the big wireless carriers and Deutsche Telekom and China Telecom, which is that narrow band over there. We can go through there. We can pick stable UI64 addresses, which ones have dense 112 prefixes. These are the networks that have the densest packed addresses that, again, if you wanted to actively scan, you could walk across it and hopefully find things in between. So that's basically it. We've operationalized this, so we're using it as an ingredient to do prefix intelligence or prefix reputation, which I think hopefully will solve some problems for us in the v6 space, where we're saying, how are we going to do what was called host reputation in the v4 address space? And then between that and v4, v6 pairings or address associations, hopefully we can, for a time, bootstrap the v6 reputation by using the v4 when we discover similar or the corresponding subnets. And if anyone has any questions or comments, I'd be happy to hear them.
Mic is open. Anybody want to comment, question?
So I had a question. So Eric Nordmark, so on the 3 days stability thing, so do we know how much of that is actually real instability as opposed to just addresses, people that aren't coming back to you, right? Yeah, and one way of looking at this might be to compare with what does it look like in the IPv4 space.
That's one of the things that a number of researchers proposed to me last week, that we would do some follow-on work, collaborating with them to use what we know about the v4 space for the subset that we think are behaving similarly. It's a good question. The classification technique is bounded by the observation point, not the behavior. So another way to do it is to get closer to those users. So if you do a measurement study where you're at the gateway for them and you always see their traffic, we could use that to frame this. But that's a good point. It's a mix of things. It means from this observation point we see it as stable or not. So it's better idea to respect the stable than the transient. The transient means maybe Akamai didn't see it again. The stable means we absolutely did.
Yeah.
Okay, so thanks, Dave. I'm going to let you drive this next conversation.
So typically before, as we get ready for meetings and figure out what our, I was just going to be here, sure. As we get ready for meetings, we look at what drafts we have in what status and figure out what we need to talk about. And anything that's been discussed, we discuss. And question that we have, though, is we have a number of documents that we haven't heard from in a while. And we need to ask the working group that have been adopted, but we haven't seen revisions. And so this is just the drafts in the working group. And we wanted to ask, I'll point out a couple in particular. We want to ask, do we want to abandon these drafts, or is there interest in the room? Is somebody going to be willing to either poke the authors or join the authors and help bring these back to life and get some revisions so we can make some progress on them? Working group said at one point we wanted to adopt these, so they're working group documents. We need to decide what to do about them. So for instance, we have this one, mobile device profile, right?
So that's in the
that's in the
Neville Brenly's.
Okay, good, thank you. So the status hasn't been updated here. And we have this one, right? The EULA usage recommendations. We sure had a lot of active conversation about the recommendations on ULAs, and we haven't had a revision in a while. Is there still interest in discussing this? So I'm not seeing anybody going to a mic to say, yes, I am dying to work on this. So I'm going to ask for a hum. Actually, I'm going to ask for a hand to say, is there anybody in the room who would like to work on this document some more? Contribute language. We'll take it to the list to confirm, and because if there's anybody on the mailing list who wants to work on it, then we may still, we'll bring it back and see if we can get some action. Without an author who's actively working on it, we're not going to make any progress. What was the third one? Oh, yeah. Another one, the DHCP v6 Slack problem, where we had a lot of conversation for a while and haven't seen anything in a while. Is there anybody in the room who would like to work on this document some more? See if we can come to consensus. Given the lack of anybody willing to contribute to the document, we'll take it to the list and see if anybody there is willing to work on it. And if we can't find an author or anybody willing to take up the pen, we would abandon it. Does anybody disagree with what I'm proposing to do? Okay, thanks everybody. Do we have anything else on our agenda today?
That's the end of the agenda.
We're going to be looking for our blue sheets back. Thank you.
Blue sheet.
Nap?